Hello, Mr. Claudia here, and today we have one of our last calculus lessons for a long while. We're going to be tackling the granddaddy of all calculus applications, which is a full-on optimization problem. And you're going to find that actually the math today isn't the worst part. What makes today a difficult lesson is that you're going to need to analyze word problems. So there's a lot of links in this lesson back to some of the word problems we started you off with in grade 9. And you'll find that these are kind of the hardest word problems you'll get in your high school math career. So it's a two-part lesson, two-day lesson. We're going to start off small and work our way up. But just as an introduction, let's say you're designing a can for Coca-Cola that has to hold 355 milliliters of liquid. Your Coca-Cola, you want to make sure you save every penny, right? Because you're making billions and billions of cans. So you want to choose dimensions that will minimize the surface area. Surface area is, the exterior of the can. It's basically analogous to the material, right? The more surface area you have, the more aluminum you need. So you want to minimize your surface area, then you can minimize your material, and you can make lots more money as a Coca-Cola brand. So, okay, one option would be to make a tall and skinny can. If you think of this thing, it holds, the version of it that holds 355 milliliters has a very small radius, but really tall. So actually, it's using a lot of material. Conversely, what you could do is make like this short and wide can. Again, it would hold 355 milliliters. The dimensions to make this happen, it's very short, 2.48, but it's very, very wide, 6 over 6 centimeters. So again, it's using a lot of material. So there's actually some in between that is optimal. That is the minimum amount of material. It's where you get the 355 milliliters, but you have the least amount of surface area. So that's what we're trying to do today. This is a large surface area. This one is a large surface area. And this is our optimal solution. It's a kind of a, it's just right. Now, how are we going to do this? Well, we're going to essentially be making a graph. So this is a function for area as a function of radius. So this is the radius, and this is the surface area. So as our radius goes up, we start off with a really high area, then we drop down to this optimal point, and then as the radius gets really, really big, well then actually the surface area starts increasing again. So what we're trying to find is this function, and then we're going to perform some calculus on it to find the optimal value, the minimum surface area. So the trick today is not necessarily finding this point. I mean, you know what this point is. It's where the derivative is equal to 0. The problem today is going to be actually finding the equation of the function. So, now, over the past few lessons, you've gotten comfortable, with finding the max-min points, and of course, looking at extreme values and using the second derivative. Today, it's more about the word problem. So let's go through the strategy that we're going to use to do this, to do an optimization problem. Most important thing, understanding the problem. It really helps to always draw a diagram just to understand it, to put the words into something, some sort of meaning. Then we write a let statement to define the quantity being optimized, so the thing that's being maximized or minimized. For example, in this Coca-Cola example, we were trying to optimize area, surface area. So I would say let A equals area. Then we need to write another let statement for any other variables. So in this case, I guess I'd probably have a variable for height. H is equal to height and R is equal to radius. Those aren't the things being optimized, right? Area is being optimized, but those are the other variables that I would need if I was defining a can of Coke or Pepsi. Okay, write an equation for the variable to be optimized. So again, this previous example, I'd write an expression for area. Then I would substitute in any additional equations so that the variable is expressed in terms of only one other variable. So usually for the area of a cylinder is A equals pi r squared. Then we have pi r squared again, and then we have, what is this, h2 pi r h, I think, for the area of the kind of curved part. So that, anyways, whatever it is, that includes r and h. So then I would need to sub in another equation to try to get rid of one of those variables. And we'll show you how to do this in a problem. It's a lot more clear if we do an actual problem. What you eventually are going to do is get a function of with your thing that you're trying to optimize in terms of one other variable. And now it's just a simple case of finding the derivative and finding those critical points. So finding the points where the derivative is equal to 0. That's just going to correspond to a max or min point. And then you actually, this part here is very similar to what we did yesterday in the extreme values lesson. You're going to have to eliminate extraneous values. So you're going to have to make sure that you don't have a negative value if you're looking at time or a negative area. You're going to ensure that you have the absolute max min by comparing with the interval endpoints. That's what we did in our last lesson. And then you might even want to check your solution using the first derivative test or second derivative test to make sure the answer you found is actually a max or a min. So these two points actually we were training in our last two lessons to do. Let's put this into practice. We'll see how it's not actually that bad. We have 2 days worth of questions here. So I'm going to go through example 1, 2, 3, and then you actually have some homework to go through that goes with that. 4, 5, 6 you can go through on your own. Usually I do these in class in small groups. I will post the answers to these with the rest of the lesson. And then day 2, we'll do a few examples together. And again, you have some to work on your own, and you have some homework. So it's all going to be one long video. You're going to have to fast forward to the right sections. Okay, so let's start with our easiest example here. Find two positive numbers whose product is, 10,000, and whose sum is a minimum. Okay, cool. They're such short problems. So let me get a new sheet of paper. We're going to need lots of paper today. Okay, and we're going to put, what is this, 9.3c, page 3. Okay, so this is number 1. Okay, first step. Now this is a word problem. Understand the problem by drawing a diagram. Not a great example for a diagram, so I'm going to skip that. Writing a let statement to define the quantity to be optimized. Okay, so I'm looking for two numbers, and the product is 10,000. The sum is a minimum. Okay, there's the clue. It's telling me that the sum has to be minimized. So that's the first thing I'm going to say is let S represent the sum. This is step 1, right? Okay, let S represent the sum. And I'll just, for now, just because we're just starting here, I'm going to make this nice and really illustrate what we're doing here. S is the thing we're trying to minimize. Okay, great. What other things are we looking for in this question? Okay, what other numbers can I define? Oh, well, I'm looking for two positive numbers. So why don't I define those with variables? So I don't know, you can choose whatever you like. Let's use X and Y. Okay, so I have a bunch of numbers, or I have a bunch of variables. Now, let's write an equation for the variable to be optimized. I want to sub in a bunch of things until I have the variable to be optimized in terms of only one other variable. Okay, so the variable to be optimized is S. As we know, S is the sum. Okay, so the sum, S is equal to the sum of X plus Y. Now that's a great expression for sum. But remember, this is no good to me if there's two variables. I can't take a derivative if there's two variables. So I need to sub in another equation to get rid of one of these variables. So I have to go back to my problem. Is there any other information that allows me to make another equation? So two positive numbers, their sum is, oh, their product is 10,000. So the two numbers multiply to make 10,000. Well, that is just the other information I was looking for. 10,000 is equal to x times y. Now I just need to combine these two equations. Now, unfortunately, I have to rearrange. So how about I rearrange in terms of y? So I'm going to get y is equal to 10,000 over x. So now I have an expression for y. I'm going to sub it in. So I end up with s is equal to x plus 10,000 over x. Remember, this was my goal. This is my key point. The hardest part of the question is I need to write an expression for the variable to be optimized in terms of only one other variable. Now I can move on to step 3, find the derivative and all critical points. And this should be second nature. We're trying to now take our function and find this minimum or maximum point, which is where the tangent line is 0. So let me take the derivative. So this is going to be ds dx, or however you want to write the derivative out. Okay, what's the derivative of 1? Or of x? Oh, it's 1. What's the derivative of this thing here? Well, this would be x to the minus 1. So if you can imagine, the minus 1 comes down. So this is minus 10,000 x to the negative 2. I kind of skipped a step there. Should I write out that step? I guess so. X plus 10,000 x to the negative 1. Maybe that makes it a little bit easier. So I rewrote it like that. And then, okay, to take the derivative of this is 1. Derivative of this, negative 1 comes down, and this becomes negative 2. Okay, anyway, so now I have a derivative. Now we want to find out where the tangent line is 0. So I'm going to set ds dx equal to 0. So if 0 is equal to 1 minus 10,000 over x squared, technically. I'm going to bring this to the other side. Then I'm trying to solve for x. The best thing I think I can do now is cross multiply. So I get x squared is equal to 10,000. And then I need to take the square root of 10,000. But remember, when you take the square root, when you undo a square, you have to take the plus and minus. So let me do the square root of, well, we should know what this is. It is 100. So the answer is plus or minus 100. Or is it? Okay, well, first of all, I think it said in the question two positive numbers. Okay, so here we go. We can validate some of our solutions. So, oops. Negative 100 is an extraneous solution. Right? You can't have a negative positive number. So it looks like it's x equals 100. Do you want to check with the second derivative? I mean, we could even check to make sure that x equals 100 is actually the min point. Now, again, IB doesn't really need you to do this. Usually they'll ask you to, but let's just show you. So I'm going to take the second derivative. So where's my first derivative? Somewhere up here. So the derivative here is going to be 0. This is going to be plus 2 times, plus 2 times 10,000. What have I done here? And then it's x to the negative 3. Sorry, this got so weird. But I end up with 20,000 over x cubed. Now, to check with the second derivative test, if I check the second derivative test at this value, x equals 100, remember, if it's positive, it's actually a minimum. If it's negative, it's a maximum. So let's see what the second derivative is at x equals 100. So it'd be 20,000 over 100 cubed and it's 0.02, which is greater than 0. Therefore, x equals 100 is a relative min. So that was the second derivative test. Not necessary. Usually in an IB question, it'll be stated that you have to do this, but I'm just showing you how that step would work. The other thing that was in our algorithm was, and what we did it yesterday, could you check the intervals? Well, there aren't really intervals in this question, right? It's not like it's specifically saying that, oh, you have to check the, there's a max number, a min number. You kind of can have any number, so we don't really have to worry about the intervals. The only thing that we have to do now, and hopefully set it here, we just have to make sure we're answering the question that was asked of us. So the question said find 2 positive numbers. Well, I did not find 2 positive numbers, I found 1. What is my other number? Well, remember at the beginning, x and y were my 2 numbers. So I know what x is, I have to find the y. So, oh look, I have an equation here that gives me the corresponding y value. So I'm going to just do that over here. I'm going to sub x equals 100 into y equals 10,000 over 100. And that gives me 100 as well. So therefore, the 2 numbers are 100 and 100. And there you can answer a very unnecessary little riddle. What are 2 positive numbers that add to 10,000 and have a minimum sum? It's great. Cool, so that's how optimization works. Really, the derivative isn't the worst part, right? It's the hard part is making the equation. So let's move on to kind of a more practical question. We'll go into question 2. So I'm going to take this page and get rid of it. Question 2. A farmer wants to make a fence pen for his horses. The pen will be along the river, so only 3 sides of fence will be needed. That wily farmer is trying to save on fence costs. He has 1,600 meters of fence. Find the dimensions that maximize this area. So we get a question like this. First of all, I'm just going to get a new sheet of paper and I'm going to write 9.3c. What is this? Page 3. We're doing question 2. Okay. So first of all, it really helps to draw a picture because it's hard to understand what's going on here. So you have to imagine, what did the farmer, he wants to make a place for his horses along a river. So he's got like some sort of river on his property. This is a big river. And then he's going to make a pen for his horses. So he's going to make, some space like this. I don't know. It's going to look something like that. Immediately it's starting to take shape. So he's saving some money. He doesn't have to put fence here. Hopefully the river is big enough that his horses can't jump over it. Okay, now I've got a little bit of an understanding. Let's go back to the question, back to my strategy, which is now to write a let statement for all the variables, starting with the variable to be maximized. So step 1, what am I trying to maximize here? The farmer wants to maximize the area. He wants to give his horses lots of space. So let's let A be the area. And again, if it helps, and I can find my red pen, maybe put a box around this, right? Just to remind yourself, this is the thing. This is the thing I'm trying to maximize. Okay, now we need some other variables. So what are the other things that I'm looking at with this picture? Well, so there's the area. Well, to even find area, I need to know the dimensions. So let's call this dimension W and this dimension L, length, and then this again will be width. So let's just define those. Let L be the length of the pen and W be the width. So now I've defined all of the variables. I mean, you might define, that should be enough, hopefully. But you can tell the picture really helps. Okay, so now step 2, I need to write a function for the variable to be optimized. So step 2, I'm going to write a function for area. So how do I calculate area of this pen? Well, it just so happens I have these 2 variables, length times width. So area is equal to length times width. Now that's great. I have a function for area being maximized. However, I got a problem. There's 2 variables here. So I need to use some other information from the question to make a second equation. Let's go back to the question. Farmer wants to make a fence pen. There would be 3 sides along the river. Oh, there we go. 1,600 meters of fence. Well, 1,600 meters of fence is kind of the length of fence. So for this one, let's think about the length of fence, or the perimeter of fence. I have 1,600. This is equal to this length, and this length, whatever they are. So it would be 2w plus L. W plus W plus L. Sorry, you can't see. So that is my second equation. Now, I need to rearrange this so I can sub it into this. I'm going to do this in a way that makes the easiest expression. So it makes sense to leave the L by itself. So I end up with 1,600 minus 2w. Now I have an expression for L. That's what I'm going to sub in. So I end up with area is equal to 1,600 minus 2w times w. And that's a little bit of an annoying expression, so let me just expand this. And I end up with 1,600w minus 2w squared. Again, we've done it. That's the hardest part of the question. I now have a function in terms of one other variable. So now this is not a difficult problem to solve. If I want to find the optimal point, that is the max point, I need to find the derivative. So the derivative of this function is 1,600 minus 4w. What do we do now again? Oh yeah, I want to find where the derivative is equal to 0. So set the derivative equal to 0. So I end up with 0 is equal to 1,600 minus 4w. To solve this, I'm going to isolate. This is just a linear expression. So w is equal to 400. Oh, wow, look at that. Now, I do need to kind of validate my solutions. In this case, there's only one solution. One thing you could do is check the second derivative test to make sure it's a maximum. You could do that. I'll just show you how the intervals work in this case. So again, this is maybe not something that you'd always have to do. I find that IB questions, you kind of tend to expect you to be done at this point. But it is possible, and they've said in the curriculum, it is possible that it could be endpoints. So I'm going to check the critical points and endpoints. So I have my area at 400. So that's going to be, that was my critical point. So I'm going to sub that in. That's going to be 1,600 times 400 minus 2 times 400 squared. So that would give me 1,600 times 400 minus 2 times 400 squared. Oh, that gives me a big area of 32,000,000. Now, what are my other endpoints here? Well, one endpoint would be a width of 0. Can you imagine that? I mean, it's kind of theoretical, but technically you could have it where it's an infinitely long pen. So it's very tiny width and then a very, very, very long pen. So width of 0. If I sub that in, I get 1,600 times 0 minus 2 times 0 squared, which is just 0. And then what would be the other endpoint? Well, the other endpoint would be if I use all of my fence to make the width. So I have 1,600 meters of fence, so I could have 800 and 800. So you'd have this kind of very long, very thin river, or thin pen. So you'd have 800. This would be 600 times 800 minus 2 times 800 squared. I'll do a quick sketch to explain this, but let me just check my solutions here. And that gives me an area of 0 as well, so it wasn't either of those. Let me just explain a little bit here. So this endpoint would be, let's call this one endpoint with width equals 0. Very long pen. So if you can imagine, it would be something like that. And this one would be the endpoint with W is equal to 800. Very thin pen. Right, because it would look something like this. 800, 800. And this was going to be what? 6, 0. 1600 and 0. And so we see for this kind of check, we kind of see that we don't have to worry about these being max points. The maximum is truly the number that we checked. It's the number that we found, that critical point. As I said, in IB, frequently this isn't necessary to do. It's usually the point that you found, but you know, it's possible. So, what was the question again? Find the dimensions that maximize the area. Well, I've only found the width, so I also need to find the length. To find L, sub in W is equal to 400. So I'm going to take my expression for length, which is up here. So I have L is equal to 1600 minus 2 times 400. That gives me 800. So therefore, the max pen area occurs for a length of 800 meters and width of 400 meters. So you can go call your farmer and tell him that's the dimensions you have to use. That's going to give your horses the most area. Terrific. Okay, let's put that one aside as well. And let's continue with a third example, and then we'll have a few more questions for you to work on your own. Where's my lesson? Here it is. Okay, here. An open box can be created from a sheet of regular paper by cutting 4 identical squares out of the corners and then folding the sides up. If the dimensions of the sheet of paper are 28 by 21 centimeters, what is the maximum volume that can be created, and what is the dimension of the box? Okay, so this can be a difficult problem to kind of visualize. I'll try my best here. Let's get a new sheet of paper. This is going to be 9.3C page 5. Wow, we're flying through this. And we're doing number 3 here. Okay, so let's just try to visualize what they said. So they said, okay, we're going to take a regular sheet of paper. And okay, it was what? I think the dimensions were 21.5 by 28 centimeters. Okay, and we're going to cut 4 corners out of the page. Okay, what did it say again? Let's just go over this again. It said, an open box is created from a sheet of rectangular paper by cutting 4 identical squares out of the corners and then folding the sides up. So this can be hard to visualize, but you're going to take your sheet of paper, you're going to cut out these 4 identical corners, and then you're going to fold up these remaining flaps, and you're going to make a box. I do have every year I take out my folding activity here. So let me zoom out a bit. So here's a sheet of paper, and see I folded, get rid of, so you have a nice background. I cut out the same identical sized corners. Now I'm going to fold up these flaps. It's like origami with Mr. Karate now. And I make this kind of box, right? I make it's kind of like a little tray. Well, it's hard to see, it'd be really easy in real life, but you get an idea. So this open box, this tray, what would be its volume? Well, it's not very tall, right? So it's got a pretty small volume. But I imagine, well, what if I made these cuts bigger? Then the flaps would be higher, so I'd actually get more volume. And so if I make these flaps bigger, these cuts bigger, probably going to have more volume. But then, like, if, in the other extreme, if I take a sheet of paper and I cut out 4 identical squares from each corner, but they're enormous, and then I fold up the flaps, well, I end up with, like, oh, this origami experience doesn't look so good. But I end up with this box, and it's like, it's very tall, but very thin. Like, so it actually doesn't have a very large volume either. It's pretty small volume. I've actually done this activity where everyone gets a different size square to cut out, and then we all make the boxes, and we actually measure which one has the largest volume. But you can imagine, and we're going to do it with calculus, you can imagine it's something in between these two. Like, say this is 1 centimeter, and this is what, like 7 centimeters, somewhere in between. So the question is, what is that cut that's going to give me a maximum volume? So origami is over. Fun part's over. Let's do the calculus. Now, the real problem, as I told you in today's lesson, how do I write this equation? So I've got my sketch. Let's start by following the steps. The first step is, what is the thing you're trying to maximize? Well, the question told us, and we were just talking about it, we want to maximize volume. So let's let V be the volume of the box. Again, you don't have to do this, but it's kind of nice at the beginning as we're getting used to this. I'm going to put this in a big red square just to kind of keep my eye on the prize. This is the thing that I'm trying to maximize. Maximum volume. Oh boy. Okay, so what are the other variables? Well, let's just think about the box that you're drawing. And would it help if I draw a little sketch here? Like, it's going to be, you know, first year engineering drawing class. Hopefully pays off. Something like that, right? It's a box. Ooh. Okay, so how would I find the volume of this? Well, if you can imagine, there's a, you know, a width to this box, a length to this box, and then from grade 9, you know, math, you remember there's a height to the box. So let's actually just define those variables, right? Those are the variables I need. So I have, let h be the height of the box. Let's let L be the length, and let's let W be the width. Oh, how does that translate to my life over here? Well, if you think about it, your width, like, is the part that you fold up. So the width is actually going to be here. Maybe I'll do this in a different color just to accentuate the difference. So this is the width. This is the part that folds up here. This would be my length. This is the inside. This is the length. And what about my height? Well, if you think back to what I was doing here, the height of the box had to do with the amount of cut. So if I've cut this much out, that cut actually becomes the height. So it would actually be this amount here. Or you could even say this side, right? Because we know it's a square. This is going to help us when we get to part 2, which is write the equation. So remember, I need an equation to optimize V. So how do I find the volume of the box? Again, you should remember from grade 9 math, it's length times width times height. Now this is great, but the problem is I have 3 variables. I need to use some more information. But fortunately, I have lots of information. I have, look at my diagram. This is where the diagram really helps. The length is equal to, okay, well, 28 is equal to height plus length plus height again. Right, because this is also height. They're all identical squares. So here we go. I have 28 is equal to 2h plus L. Or in other words, L is equal to 28 minus 2H. Similarly, W is equal to 21.5 minus 2H. So using my diagrams and some thinking, I'm able to get these two expressions, one for L, one for W, and I can sub them back in to the expression for volume. So now I end up with, I'm just going to have to squeeze it here, 28 minus 2H times 21.5 minus 2H times H. Now, it may look like a mess, and it's horrible, but look what it is. It's a expression for V in terms of one variable, H. The only problem is it's a little messy. It would be hard to take the derivative of this. Because I know I have to take the derivative, I am going to expand it. Because I used real world numbers, you're going to have to use a calculator because it's a little awkward here. So I have 28 times 21.5. 28 times 21.5. That gives me 602. Then I have 21.5 times 2 plus 28 times 2, so I get 99, so they're both minus, so minus 99h, 2, so plus 4h squared, and that was all times h, so I just expanded. And then I end up with 602h minus 99h squared plus 44h cubed. And that is the hardest part of the question, because now I have a function v in terms of h. So now this is just a problem that we would have done a few days ago. I just need to find the max min point. How do I do that? Well, I need the derivative. I need to set it equal to 0. The derivative here, dv dh, is equal to 602 minus 99 times 2, which is 198h, plus 12 times h squared. Now to find the critical points, I'm going to set that derivative equal to 0. So I end up with 0 is equal to 602 minus 198h plus 12h squared. So what I do need to do is, I can rewrite this. Now, well, I know what you're thinking. Oh, that's going to be really hard to factor. Just going to run over and get my calculator here. But that's really hard to factor. I don't know if I can factor that. It's true. You shouldn't factor. In fact, if you're doing this question on an exam where you have access to your calculator, it would be a huge waste of time to factor by hand for something that's this complicated. You should immediately be going to your GDC and using the quadratic formula. Okay, so I'm going to show you how to do this on your GDC. So hopefully you remember how to do this. To get to the quadratic, to solve a quadratic, you're going to go menu. Menu does all the things that are related to math. This is not a calculus thing, right? This is not a probability thing. This is an algebra thing. Let me check. Yes, it has a polynomial tool. Find the roots of the polynomial. This is the key, right? This is what allows us to solve the quadratic. It's degree 2, so that's okay. And then I have to enter the 3 coefficients. And look at how it asks you what the coefficients are in order. So the coefficient of x squared is 12. Coefficient of x is negative 198. And the coefficient, the constant is 602. I press enter. And then it gives me a line of code. I press enter to that, and it spits out the numbers. So see how quick that is? You end up with 2 numbers, and you also would never have gotten this by factoring. You would have had to use a very long quadratic formula. So you end up with this number and this number. Okay, so 2 numbers? That's not great, huh? You could have a height of 4 or a height of 12. I mean, you could think about this really hard. 12, a height of 12, if you have a box that's, or if you have a length that's 21, well, if I use a height of 12 and a height of 12, it's kind of impossible, right? Because the length here, 21, is not enough for you to cut out 12 twice. So it's clear already, and it could be clear to you, that this is extraneous. 4 seems more possible. So if you can throw that out with some logic, that would be okay. But here, I'll put an X through and say extraneous solution, because width equals 21.5 minus 2h. So that would be problematic if I used h is equal to 12. But another way you could check is by finding the second derivative, right? And you could test which one of these is a max or a min. So why don't I do this? Might as well, right? I mean, we kind of know the solution, but I'll check. So I could check my answers with the second derivative test. The second derivative, d squared v dh squared, would be negative 198 plus 24h. So now I need to check the second derivative at h is equal to 4.02. And that's equal to negative 198 plus 24 times 4.02. That is negative 198 times 24, oops, plus 24 times 4.02. That gives me negative 101.52, which is less than 0. Therefore, if it's negative, it's actually a max. So this is a relative max. And then we also want to take the derivative at h is equal to 12.48. We've already discussed this is a problematic one, but let's see what happens. This gives me 101.52, which is greater than 0, which, if we remember, that would actually be a relative min. So there we have a kind of more explanation why we don't want to use this this point. It's a critical point because it's a relative min. It's the min area, or min volume. So we clearly want to use this one. So again, you don't usually need to do this, but you can just see kind of the practical way it can be used. Or you might get a question specifically asking you to use the second derivative test. You can see how it really maps out which one's correct. Similarly, you can use the endpoint. You could check the endpoints. So an h equal to 0 and an h equal to, what would that be? 10 3/4 or whatever, to see if what the minimum or what the endpoint volumes are. We're not going to do that. They both tend to be turn out to be 0. But again, that's another check that could be done if necessary, or if you're asked to do it. So actually, the only thing to do now is to check, what was the question asking? What is the maximum volume, and what are the dimensions of the box? So I'm gonna do a few steps here. Squeeze them in. I need the dimensions of the box. So for h is equal to 4.02. The L is equal to, let me use that expression I made for L, 28 minus 2h. So I have 28 minus 2 times 4.02. 28 minus 2 times 4.02. That is 1996, a great year. And we need to find W, which is 21.5 minus 2 times 4.02. That's 21.5 minus 2 times 4.02, and that gives me 1346. Another great year. Not a great year, I don't think. So now we have the dimensions of the box. The dimensions of the box are, I guess, should be 3 significant figures probably. So 20.0 centimeters by 13.5 centimeters. And the volume, well, the max volume is, oh, I didn't quite do it yet, so, oh, this is actually times 4.02. I should give the height as well. Oh, what a mess this has become. So I have the length, width, and height, and the max volume. Let me just multiply those numbers together. So 13.46 times 1996 times 4.02, and I get 1080 centimeters cubed. Great. So that's, you can now impress your friends. If you want to get the largest open box from a sheet of paper, this cut that you're going to make is actually only going to be 4 centimeters. And then you've got the most volume. That's great. And you can use it to hold, some baseball cards or whatever you want. You can hold a lot of baseball cards. Okay, so that is 3 problems from the first day that we've done. Hopefully you've gotten an idea of how this works. There are 3 more problems for you to work through, and these are a little trickier. I will post the solutions. And you can work through with your friends. And there are some homework problems as well. So you've got lots of practice to work on. Tomorrow we're going to come back with even harder optimization questions. Okay, so hopefully in that short pause you had enough time to finish the previous problems, do some of the homework problems for day 1. Now we're ready to move on to our second day of optimization. We're going to do some more difficult problems, but not that much more difficult. First up, we're going to do a kind of a mini talk here about optimization in the business world. And you're going to have to put on your CEO thinking caps here, and imagine you're responsible for running a business, and your goal is to maximize the profits and minimize the costs. That's kind of your responsibility to your shareholders. So we have a few definitions from the business world. The first, which you might have heard before, is revenue. Revenue is all the money coming into the company. So it doesn't really consider how much money you're making in terms of profit. It's just how much cash is coming in into your cashier. For example, if you're selling, you calculate with price per unit by the number of units sold. For example, if you're selling dishwashers at $300 each, and you sell 10 dishwashers, well, your revenue would be $300 per dishwasher times 10 units, $3,000. Now, that's not how much profit you made, right? The profit is the extra money you have after taking that revenue and subtracting out your costs. So if you made sure on those 10 dishwashers you made, was it $3,000, but then you might have spent $15,000 to make the dishwasher. So your profit is 30,000 minus 15,000, which is 15,000. Revenue and profit are different, and this can get conflated sometimes. Like, think about, well, at the time of recording, the company Uber, which is the online taxi app. They make a lot of revenue, right? Millions of people are using their services. They're taking taxi rides for anywhere from $5 to $50. So they're making a lot of revenue. But Uber has a lot of expenses. The drivers, all the programmers, all their offices. So they actually lose money on every ride. So even though they're making millions of dollars in revenue, billions of dollars in revenue, they have higher costs, so their profits are negative, and their profits have always been negative at the time of writing. So I don't know why anyone would buy Uber stocks or invest in Uber. It's a company that's losing lots of money. Anyways, let's talk about, let's do a business example. And we'll try to apply some of these concepts. When you get a business example, you might find that they actually might even just give you the function, and then you just kind of do the derivative. Or you might have to do some thinking and use some of these concepts. So really be careful when you get a business problem that you're reading it carefully. And then one day when you're a consultant for one of these big companies, you would actually be creating the functions yourself. You'd have to analyze the costs and the prices and the profits and kind of write equations based on all the different factors. So, but for today, we'll see if we can build the functions using what we're given. So let's do example 7. When a manufacturer makes X items per day, the cost is this. So again, this cost might be high or low depending on depending on different factors, labor, the cost to heat the factory, stuff like that. And the price function is this. Now the price function changes depending on how many items you have. So if you have only one item, it's a higher price. If you have more items, you can actually afford to charge a lower price, because of economies of scale in your manufacturing, I guess. Find the production level that will maximize profits, knowing that the manufacturing facility can produce no more than 315 items per day. Okay, so that's kind of the max. I guess there's a production line can only move so fast in a day without building a new factory. Okay, so let's do this problem. Let's get a new sheet of paper. Let's call this 9.3c, page 6. And this is number 7. Okay, now first things first, I would want to draw a sketch. Kind of hard to draw a sketch. And in fact, I'm probably going to just lean on those formulas and discussions we talked about earlier. At the very least, I should define the variable I'm trying to optimize, which is, remember, trying to maximize profits. So let P be the profits. I guess it's profits per day, because the cost function is per day. So, and this is the thing that I'm going to maximize. Now, it would be hard to draw a sketch. I'm actually going to kind of lean on my profit idea here, which is the amount of money I make, or the money in, or the revenue, minus the costs. So let's just kind of write out in words here to try to understand what this is. So profit is equal to the revenue, which for those non-business people is the money in, money coming in, minus the costs. Okay, well, the costs we have an actual function for. The money coming in is, okay, well, this is the price per item. So it really depends on how many items I sell. So P is, this is my price. So the profit in one day is going to be the price per item times the number of items minus the costs for, we'll call this X number of items, and this is the cost for X number of items. It's kind of hard to, these are different, right? This cost function is where you just sub in an X value. So say you have 100 items, you sub in X equals 100, it's going to tell you the cost of making 100 items. The amount of money you make, though, is, well, the price that you sell each item for. So if you have 100 items, you're going to sell it for, what, 14 something. But then you actually have 100 items. So you take this price and you multiply it by the number of items. So these are kind of different functions, and that's why this is a confusing question. So we end up, so the profit for, let's call it the profit for X items. So we'll call it big profit at X is equal to the little p at X. So the price times the number of items minus the cost. So if I want to sub in my values, I end up with 15 minus 0.002x, that's my price function, times X minus, and then let's put in the cost function, which is, where is it, 720 plus 4x plus 0.02x squared. That's getting there now. This is the profit function. Profit as a function of one variable x, which is the number of items. Okay, so I'm going to just simplify this now. So I have 15x minus, minus 0.002x squared minus 720 minus 4x minus 0.02x squared. Now I should collect my like terms, so I'm going to end up with, okay, negative 0.02 minus 0.002, so that's negative 0.022x squared brought those two together, plus 11x minus 720. So that's my profit function. That would be step 1. So, or actually, this is what, step 2? This was step 1. Step 3 is solving now the maximum profit. So I need to find the derivative of this, which is negative 0.044x plus 11. And then I need to find the critical points by setting the derivative equal to 0. So I end up with 0.044x equals 11. So x is equal to 11 divided by 0.044, and that gives me 250. Okay, so that means that the number of items, x number of items, to x equals 250, that's going to be the maximum profit. That's where my profit and my cost give me kind of the best value for me as a CEO. However, let's look at the question again. What was it asking? Find the production level that will maximize profits. Okay, I found it. Oh wait, knowing that the manufacturing facility can produce no more than 315 items per day. Well, 315 items per day, this is an endpoint. This is kind of giving you an interval. The factory can produce, well, I guess it could produce 0 items. That would be one endpoint. And it can also produce 315 items. So even though I think 250 is the maximum, I should check the endpoint just because maybe it's also a really high point. So I'm going to check the critical points and the endpoints. So I have the profit at 250. There's my profit function. So that would be negative 0.022 times 250 squared plus 11 times 250 minus 720. That gives me minus 0.022 times 250 squared plus 11 times 250 minus 720. That gives me 655. Okay, I should also check the profit at, well, let's just check it at 0. It might as well, right? Just to show that this is going to be negative 0.22 times 0 squared plus 11 times 0 minus 720. Whoa, that's not good. At that level, you actually lose money. I mean, it makes sense, right? You're not making anything. You're paying all your workers and your your heating for your factory, so you actually lose money. Let's check that kind of upper limit. Remember, the factory can at the most produce 315 per day. You may think, well, I'm going to max it out. It's 315. Let me do that. But if you check, let's check the number. I actually end up with 562.05. So actually, that isn't my max profit. My max profit was that sweet spot at 250. Probably at this point, 315, I mean, the numbers kind of checked it out, but what's really happening here is this factory, you're running at a max, your max, maybe you have to pay extra overtime, you have more maintenance costs, it's just, you're not optimizing your profit. So the optimal value is 250. So we've just kind of done a check, and you can see how the check was necessary there because we were given that kind of extra interval, that extra piece of information. But the question was asking, what is the production level? So therefore, the production level that maximizes profits is 250 items per day. There you go. Great. Okay, we're going to do one more example here, and I think this is kind of one of the more challenging questions, but you'll see the other questions kind of have a similar type of strategy. So if you can do this one, you can do the other one. A cable company is laying cable in an area with underground utilities. two neighborhoods are located on opposite sides of the Don River, which is 100 meters wide. The company has to connect points P and Q with cable, where Q is a neighborhood on the north bank, and it's so much 1,200 meters east of P. Costs $40 per meter to lay cable underground, $80 per meter to lay cable underwater. What is the least expensive way to lay cable? Ooh, so you have to imagine you're standing on the river, you're looking across, you want to lay some cable. It seems like it's very cheap to lay cable on the ground, very expensive to lay cable underwater. So this is getting to be a tough question. We're going to start, like I've always recommended, to start with a sketch. So let's go up here. This is 9.3c, page 100, it feels like at this point. Okay, let's get to example 8. Okay, so let's draw a sketch. That's my first step. Okay, so we're told we have some river. Let me kind of get this river drawn here. It's the Don River, I think they said. Great River of Toronto. And the river is 100 meters wide. So I can label that, right? There's my 100 meter wide Don River. Okay, two neighborhoods are located on opposite sides of the Don River that need to be connected with cable. Now Q is on the north bank of the river, so it's somewhere here. And P is on the other side of the river. Q is 1,200 meters east of P. Okay, so P is actually here. I'll make it here just to give myself some more space. So you have P 1,200 meters over. You have Q, but it's also across the river. Okay, so what's the problem here? So they want to lay some cable to connect P and Q. Remember, it was cheap to lay cable on the ground, expensive to lay cable underwater. So what's the least expensive way to lay cable? Well, you could just lay the cable directly this way from P to Q, but then it's all underwater. It's very expensive. Okay, so what you could do is lay all the cable on the ground, which is cheap, and then cross over here, and that would give you kind of the shortest crossing, but then you've actually had to lay a lot of extra cable. So most likely the optimal solution is something where you lay a bunch of cable on the ground and then cross over in a way that minimizes the cost. If you want to draw this like this, it's some sort of cable situation where you're following along the underground and then at some point you're going underwater. So this section, let's just label it. This is underwater. What was this one? I think $80 per meter. And this was underground. Oops, I didn't need the arrow there, but underground was $40 per meter. So hard. It's hard to even imagine how we'd figure this out. Let's start by writing a let statement. What is the thing we're trying to minimize here or maximize? The cost. Let C be the cost of the cable. Now, in my solution, and this is the thing we're trying to minimize. Remember, I like to draw a little box around that just to help me remember what I'm doing. This is to minimize. Now, in my solutions, I'll present two solutions to you to do this question, but I'll show you the easier solution now, and you can look at both of them. But what you can do is, really the problem here is, how far do I go before I cross? Do I go 1 meter and then cross, or do I 2 meters, 3 meters, 4 meters? So what I need to know is how long this distance is, or conversely, I need to know what this distance is. So that is, how far before Q do I kind of cross underwater? So I'm going to call this X. Now, I guess, it's hard to explain this. I think my diagram explains what X is, so I'm not going to necessarily write another let statement, but we get an idea of kind of the diagram helps me with this. And actually, if you want to kind of zoom in on this part here, we now have a triangle shape where this distance is a right triangle. This distance is x. This length across is 100. So this distance is a hypotenuse. If you use Pythagorean Theorem, this is square root of x squared plus 100 squared. That's using the Pythagorean Theorem. X squared plus 100 squared equals this squared. Okay, so let's go to 2. Problem 2. Should I show the Pythagorean Theorem? Let me show it. I feel bad now. Pythagorean Theorem. We have a squared plus b squared equals c squared. So we have x squared plus 100 squared is equal to c squared. So we have the square root of x squared plus 100 squared is equal to c. Just so we kind of remember that. And you can see why this problem is going to be hard. It's got a square root in it. We don't like square roots, but we can deal with them. So we're trying to minimize cost. So, okay, how do I figure out the cost? An expression for cost. This is my second step, right? Well, the cost is $40 times the underground portion plus $80 times the underwater portion. Okay, so what is the underground portion? Well, it's 40 times. The underground portion is 1,200 meters. Take away this x. So this is going to be 1,200 meters minus that distance that I'm crossing at that point. And then my underwater portion is going to be this distance here, this hypotenuse, which we just found. So it's 80 times the square root of x squared plus 100 squared, which is 10,000. Now look, we just did it. This was the hardest part of the question, was making an equation. But now we have an equation for cost as a function of one variable x. So I can actually do it. It's a tougher derivative, but it's a doable problem. I am just going to simplify this a little bit. 40 times 1,200, which is 48,000, of course, minus 40x plus 80. Instead of square root, I'm going to write it with, so it's x squared plus 10,000 to the power of half, just because I know that's going to make my life easier. Okay, ready to roll? Let's do it. So I need to find the derivative of the cost with respect to this x length. Okay, derivative here is 0, derivative here is negative 40. That's the easy part. Now I have a difficult derivative, plus 80. Let's do this derivative. The half comes down. I end up with x squared plus 10,000 to the negative half times the derivative of the interior function, which is 2x. So don't forget that chain rule. Should I underline it? Why not? Chain rule, it never goes away. Okay, now I have the derivative. What do I need to do now? Oh yes, I need to find where this derivative is equal to 0. If you had a calculator, GDC question, you could actually do this with the GDC, but we're doing this by hand. Let's do it the old-fashioned way. So I have negative 40. Okay, I have half here, so this becomes half. So I have 40 times 2x over half, and 80 is 40, and this is in the denominator. Ugh, it's messy. I guess I could have done this all in one step. Do I need to combine these? Well, let's just jump to what I was trying to do, which is to set this derivative equal to 0, right? Remember, I'm trying to find the min point. So let's see if this helps me at all. So I have negative 40 plus 80x over x squared plus 10,000. Okay, so I'm going to bring the 40 to the other side. Okay, this could be worse, but it could be better. I'm going to cross multiply now. So I end up with 40 times this. I really feel like I'm going down the rabbit hole. I'm going to divide both sides by 40 to get rid of that 40 here. So I end up with x squared plus 10,000 is equal to 2x. Oof, a lot of math. Maybe there was an easier way to do this. I don't know. We're on to it. I want to get rid of the square root, so I'm going to square both sides. So I end up with, okay, the square and the square root undo each other, so I get x squared plus 10,000 is equal to 4x squared. Hey, this is looking pretty good now. I'm going to bring the this x squared to the other side, so I end up with 10,000 is equal to 3x squared. And then I'm going to divide both sides by 3. So I end up with 10,000 divided by 3. So I get x, and I take the square root of that, and I get plus or minus 57.735. Oh my god, you can't see anything. I just wrote the past 20 minutes. There's my answer, 57.735. We know that the answer must be positive. Why does it have to be positive? Well, remember, x is the distance, kind of, I make the jump. So 57 meters. It can be negative. I mean, it could be negative. It would be out here then. Which doesn't seem to make much sense. So that would maybe maximize my costs. So anyways, I've done all this work. Really, it was kind of the difficulty here was not making the equation so much as doing this tough derivative. And I get to my final answer there. Now, I suppose you want to check to make sure, again, probably necessarily don't need to. I mean, this seems to make sense to me. But if I had to check, let's just go through this kind of, this exercise. Check with the second derivative test. Remember, I'm going to check to see if it's positive or negative. That'll tell me if it's a min or a max. But if you think about like taking the square root of this, where's my derivative? It's here. Oh my god, I don't want to do that. That sounds horrible. So I'm going to say, ooh, and say I don't want to do that. It is easier to check with the first derivative test. And I know every time I say this, it's like, first derivative test, did I even learn that? And it's yeah, of course you did. It's a sign chart. And instead of doing the whole table, I mean, just think of what the sign chart, what we need to know. We need to know the sign of the derivative. Oops, oh, there's a really horrible sign chart. And we know that there's like this thing at 57.735. So we want to know, okay, we've got to verify that this is a maximum or minimum. So we want to know the sign here and the sign here. Now, instead of making a whole table and everything, let's just check 2 points on either side. So check the sign using points on either side of x equals 57.735. So for example, I can check dc dx when x is equal to 57. So where is my function? It's here, right? Up here. So I'm going to sub in 57. So I get, let's start here. 57 squared plus 10,000. Square root of that times 80 minus 40 times 57 plus 48. That gives me Okay, so I need to check the 57, x equals 57 in the derivative. So there's my derivative there. I guess I'll use a slightly easier version right here. So let's start with the bottom. So 57 squared plus 10,000, square root of that. Then I have 80 times 57 divided by that answer I just found, minus 40. So I get negative 0.384. So by subbing in that number and just kind of checking it, I know that this is negative. It's kind of like a brute force way of doing this. I can also then do the same thing, but sub in a number to the right. So x equals 58. So let me do this again. It's with the derivative, so it's right here. So it'd be 58 squared plus 10,000. I'm going to take the square root of that answer. Then I take 80 times 58 divided by answer minus 40. Oh no, what have I done? 58 squared plus 10,000. Square root of that answer. And I have 80 times 58 divided by answer minus 40. And that gives me a positive number, 0.137. So let's say positive. So you can see I have this negative and positive. So therefore that confirms that 57.7 is a relative min. Okay, and what was the question asking again? We should just make sure what is the least expensive way to lay the cable? So we would tell the company, therefore we would tell the company to lay. Okay, so it was, this is going to be 57, so it's going to be 1200 minus 57.735, so 1140. So we laid 1200 minus 57.735 equals 1142.265 meters of cable underground. Okay, now I know what you're thinking. Mr. Klein mentioned you could use the calculator to do this quicker, and it's true. We could do this, like to find using the calculator. If you think about it, remember the calculator is really good at finding a number. It's not good at finding algebra, but it's good at finding a number. Now, and we even, assuming we had this question, we did use a calculator a few points. So in theory, you would, if you had the calculator, you would want to optimize your solution to use the GDC. Now, traditionally, normally, if you get a question that involves optimization on an IB exam, it'll probably be your paper 1, the one with no calculator. So you'll get easier numbers that you're able to work with. But let's say I had this question and I wanted to use my calculator to attack it. You would not make sense to do so much algebra. You'd want to avoid the algebra. Now, your calculator can't give you the equation itself, but once you found the equation, you could use this to find the optimal value. There's a few different ways you could do this. So this is kind of a little calculator review for you. First thing would be to go to graphing mode and to graph. So I'm going to press tab, graph the function that you found. So that's 48,123 minus 40x plus 80 times the square root of x squared plus 10,000. So there's my function. No, I don't see my function. Oh, my calculator's broken. No, I have to change my zoom. Let me go to zoom fit. Down here, this is usually a way you can, good starting point. Doesn't look great here, but I can see at least I've got the y values more or less correct. I'm going to change my x values. I'm going to go further in the x direction. I actually don't need the negatives because you can't have a negative x in this case. So I'm going to go menu, window zoom, settings. I'm just going to change my min x to 0, my max to, oh no, 200. Let's see what happens. Okay, oh, that's pretty good. So now I just need to scroll down a bunch. So I'm going to menu, graph entry, window zoom, window settings. Let's go my y value. Oh, they're so large, the y values. How about I go to y min of 0? Would that work? Oh my, this looks terrible. Okay, so this is from 0 to really big number. You can see we're kind of concentrated up here. So I'm going to do one more time. Menu, window zoom, window settings. The y value is too small at this time. Let me go up to maybe 4,000 or 40,000. Okay, that's looking better. So there's my graph. Anyways, I can see there is a min point. I'm going to go menu, analyze graph, minimum. It says where's your minimum located? Well, it's located somewhere between here and here. And there we go. The function gave me a minimum 57.7. So it's kind of almost cheating with your graphing calculator. You can take the function and graph it. While we're here and you're still watching this what is going to be an incredibly long video, if I were to go to a new document and make a graphing page, I could also graph the first derivative. So watch this. You could say, okay, I want to graph a function. I'm going to press this button next to number 9, and I'm going to select derivative, first derivative. And this is with respect to x. So I want the first derivative of that function, 48,000 minus 40x plus 80 times square root x squared plus 10,000. So now this is going to graph the derivative function, which, again, I can't see it. Menu, graph it. Oh no. Window zoom before. Fit. Let's go to A. And there's the function. And so what I'd be curious to know, menu. So this is then the negative. So I want to see where this function crosses the x-axis, because remember, where the derivative equals 0 corresponds to a max or min point. So I'm going to change my zoom so that I have window settings. Let's go from x equals 0 to x equals 100. And let's see, okay, the negative 49 to positive 100 or something like that. Let's see if that gives me, there we go. So I found it. So you can see where this function crosses the x-axis. Menu, analyze graph, 0. Where the derivative is equal to 0 corresponds to a max min, and there you can see it's 57.7. So those are both ways of almost cheating with your graphing calculator. That's why I would expect that if you get a question like this, it will be a non-calculator question. Okay, so that brings us to the end of this long discussion. You have 3 more questions you can do involving cost, and then some more that involve square roots, and that's more difficult derivatives. So once you finish that, you have a few questions of homework. You might want to catch up on the other questions you haven't done. Good luck with that, and we'll see you next time.